So welcome here to part two of our series on SMNRs. And last time we had Dr. Gordon Edwards telling us why he didn't think that SMNRs were a good idea for Saskatchewan. And we're going to have tonight Dr. Neil Alexander, who will be slanted more in the other direction. We'll put it that way. So in order to introduce him, I am going to ask Dr. Margot Hurlbert, who's a professor of climate change and energy and sustainability at the University of Regina, to introduce our speaker tonight. Thank you, Margot.
Great, thank you. Great, so it gives me pleasure to introduce a colleague and a longtime friend, Neil Alexander. He was in Saskatchewan. I met him at the Fedoric Center for Nuclear Innovation here at the University of Saskatchewan in Saskatoon. And we have been friends for almost a decade and both interested in nuclear energy. So Neil is an environmentalist who, having started his career in renewables, moved to nuclear because he wanted what he did to make a difference. He has, over the last 40 years, run radioactive waste management companies on 2 continents, set up 2 radioactive isotope production units, led the Organization for Canadian Nuclear Industries through its development phase, and used his position as the executive director of the Fedoric Center to support the formation of the Center for Science and Innovation Policy here at Johnson Shoyama Graduate School of Public Policy and its nuclear program. An earlier proponent of small modular reactors, SMRs, he remembers being told by a very senior member of the Canadian nuclear industry to shut up about SMRs, they're never going to happen. And he's now the part-time communications director of the Canadian Nuclear Society and an independent consultant specializing in helping people improve their communications and notably to write better commercial proposals. He's speaking tonight as an informed private citizen. So welcome, and I'm so glad to be introducing you here tonight, Neil.
Thanks, Margot. I'm just reeling from the shock of the fact that it's been 10 years already. Time flies. And the first thing I have to do is apologize to everyone for the lighting that I have. I'm looking a little stark, and I'm not sure that there's anything I can do about it. But the good news is, we're going to quickly flip from my face and hopefully share the screen. And if we can do that, we will get to the presentation. There you go. Right, good. So now you don't have the stark face on the full screen, and we can go through my slides. I did want to mention first that I am speaking to you from Ontario, on the beautiful shores of Lake Erie. It is the traditional lands of the Mississaugas of the First Credit, and very proud to be speaking from here. And as Margot said, I did used to live in Saskatoon, so I do know what it's like out in your part of the world. And my title for the presentation doesn't quite line up with the one that you were taught to, but I'm going to talk about nuclear energy, and in particular trying to focus around the small modular reactors you might have in Saskatchewan. And I don't propose to be a proponent for them. I think everybody has to make their own mind up about what's appropriate in their region, but I do hope to provide you some useful information in helping you make that decision as to whether they are appropriate. Set out an agenda for tonight, and I hope that you might indulge me just at the start, because I want to talk about conspiracy theories and how to spot them. One of the things that I've noticed about anyone getting involved in a nuclear program is that they will be bombarded by conspiracy theories, and it's impossible for anyone to deal with all of them as they come up. So what I like to do is try to arm people to be aware of them, and then work out how to spot them, and perhaps then give them the attention that they appropriately deserve. Then I'm going to talk a little bit about nuclear in general, followed by a bit of detail on small modular reactors and the ones that you may see in Saskatchewan. And then, because I think it's one of the issues that worries people most, how the fuel that is used in reactors is then used, dealt with after it comes out of the reactor. And then finally, I started out with the view that I would leave lots of time for questions. I haven't timed this presentation. Having had plenty of warning of when I would be making it, I actually got around to sorting it out sometime earlier this afternoon. So it's totally unrehearsed, and we're just going to see how it goes. So the first thing I wanted to talk about was conspiracy theories and how to spot them. And so I could tell you about one of the chemicals that is used in small modular reactors, a chemical called dihydrogen monoxide. A lot of you are probably aware of it already. I could tell you some absolutely spot-on facts about dihydrogen monoxide. It is the most powerful solvent that is known to mankind. It is undoubtedly responsible for more deaths of human beings than any other chemical that we are exposed to. Even just touching a solid of it will cause severe tissue damage within minutes. And if you're exposed to it in gaseous form, you'll burn your skin instantaneously. And so I can tell you all those facts about dihydrogen monoxide. And they did the study and did a test, just providing a few of these facts to people, and these were done in America. And I think, 86% of the population would support having dihydrogen monoxide banned. People were scared of it. I think the second study said 90% of the people would have dihydrogen monoxide banned. And I want to stress everything I told you about it is absolutely true. And I could have gone on for another 15 minutes about dangerous things of the exposure of dihydrogen monoxide. Dihydrogen monoxide is, of course, water. And I mention it that way in order to impress upon people just how easy it is to start conspiracy theories if you just pick a few facts and present them to people, and you lead them through a logic, but you're not honest about the total facts. And so you can do this, and it happens all the time. We're exposed to it all the time. And if we are to make good decisions, we need to spot these conspiracy theories and start ignoring them, or, giving them as I said, the attention that they deserve. Conspiracy theories work, as I said, just by, people picking facts from all over the place and dealing with them out of context. And the key to good decision-making is not just to focus on facts. The key to good decision-making is to understand the facts in the context. And I think as we come to some of your questions, you'll see the nuance of how you have to put those facts into context in the way that I answer those questions. I have some simple rules, and I'd like to use as an example a very silly conspiracy theory that is going around at the moment, whereby out in New Brunswick, they are looking at a couple of small modular reactors that would involve some reprocessing of the fuel in order to fuel the reactors. And the concept that this conspiracy theory has is somehow it's an entrance route to Canada producing nuclear weapons. And it's difficult to actually pin down the conspiracy theory because it moves around, and sometimes the government's doing it, and sometimes some evil landlord is, taking over the plant and he's going to do it. But let's focus on the government side, because that's the only one that's credible. I mean, frankly, the idea that somebody would move into a nuclear plant and be able to siphon off the products from it is so unbelievably that if you took the plot to Cubby Broccoli as an 007 movie, he'd say, can you go away and come back with something a bit more realistic? Let's talk about the government then. So I have these rules. So you have a look at why would they do it? Well, if the government was secretly trying to produce nuclear weapons, there would be no benefit. Nuclear weapons are a deterrent. And if you don't tell people you've got them because they're a secret, then they are of no value to you. They also would have no value to Canada because there is no enemy that we could deter with them. unless we are contemplating having the Russians die laughing, because the only people that we would be in a war with nuclear weapons with have arsenals that were way larger than anything that the plant that is being proposed in Canada, even if it would repurposed, could make any difference. You then go to the practicality of could they do it? Well, actually, technologically, they couldn't do it. They've woven some story that says, well, if you did this and if you did that and if you did the other, then it would be possible. But actually, none of those things could be done because we'd be spotted doing it and stopped. So that's one of the reasons that technologically it couldn't be done. But actually, it can't be done simply from a government changeover point of view. I mean, I don't think even Justin Trudeau believes that he is going to be in power for the next 15 years to see the project through to a successful conclusion. So at some point, the government's going to turn over and somebody's going to say, hang on, you're planning some secret nuclear weapons there, and they might kind of spot it, right? So there's no practicality behind it whatsoever. And then the final thing I look at is, if they got caught in the middle of this conspiracy, what would be the result? Well, the instant that anybody thought that Canada had any prospect of producing weapons-grade material, we would have embargoes on all our trade from every nation in the world. We would become a rogue state like North Korea, and our economy would instantaneously shut down. There is absolutely no benefit to it whatsoever. So without even addressing the facts, if you look broader than the conspiracy theory and put it in context, you go, this is just nonsense. And the sad fact of the matter is that people are putting this conspiracy theory out there, even though they know it's rubbish, because they want to try and drag SMRs into the nuclear weapons debate because they think they can win that debate. And basically they're losing the SMR debate because most of what they said about them simply hasn't turned out to be true, and people are beginning to recognize it. So anyway, you don't have to do that just on nuclear. You can use this for any conspiracy theory that you hear. Just ask yourself these questions, and it will typically lead you to a decent conclusion. So I'm just going to talk a little bit about nuclear. I think probably most of you are aware that there's a fair amount of nuclear power generated in Canada, most of it in Ontario, historically some of it in Quebec, and an ongoing operation out in Point-Lepreau in New Brunswick. About 15% of Canada's electricity comes from nuclear power, and in Ontario, it's something around 60% of the electricity that comes from nuclear power. So it's a very significant power generator for Canada as a whole, and it's extremely significant in Ontario. The Ontario economy has basically been built on the back of the energy that has been supplied to it from the Ontario nuclear fleet. Many of the reactors are presently being refurbished and will then have an ongoing additional life of another 30 years. So that fleet is going to be around producing power for some time. When I made this slide originally, this is one of the slides I did have to update. There was a plan to close the Pickering plant, which is the oldest, and not to refurbish it. But now, recognizing the challenges of dealing with climate change and the power demands within Ontario, Ontario Power Generation that own the plant have been asked to go back and reconsider and to see whether they can cost effectively refurbish that plant. A lot of people will say that the nuclear industry can't deliver any projects to time and to cost. In fact, if you look at projects as a whole, what they call mega projects, and the big nuclear plants are mega projects, then nuclear fits fairly comfortably into the middle of the fold. Human beings, for some reason, have a problem delivering mega projects. The largest projects that are taking place, infrastructure projects that are taking place in North America, two of the largest are in Ontario. They are both nuclear projects. One is the Darlington refurbishment and the other is the Bruce Power refurbishment. As you can see from this headline, which I think was late last year, probably full last year, that these projects, which are immensely complicated, far more complicated than building a new plant, are presently running to time and to cost. So nuclear industry is demonstrating that it can deliver these projects, even if they are mega projects. And some of the units have been restarted. So it's not just we're halfway through hoping that the other half is easy, that they're polishing the units off one after the other, and they are being reconnected, having had their project done appropriately to time and cost. And that I'd forgotten that. Another thing I wanted to say about the nuclear industry, we're very focused on it for its primary task, which is producing greenhouse gas-free electricity. And that is obviously an extremely important deliverable for the world at the moment. But actually, the byproducts from the nuclear industry are absolutely essential to keeping our world turning. And Margot may have had to suffer me on the subject here, but the last time I got going on this, I spent an hour and a half on the other things that the nuclear industry does that people are blissfully ignorant of. Actually, I do a working day of my own, and I step outside of my bedroom and face a smoke detector. Most domestic smoke detectors contain americium-241. Americium-241 is chemically and radioactively very similar to plutonium, and we use it to save people's lives. They are one of the most powerful. I mean, we are mandated to have them in our house because they save so many lives. We use them to inspect the jet engines in planes. We use them to inspect the structural steel in our tall buildings and in our bridges. Without that, they would be at risk of decay and collapse. We use them in materials research that is essential to improving the efficiency of the things that we do, and that has knock-on effects to reducing our gases. They are used to keep food safe. We irradiate spices because any other process to deal with pathogens in spices would destroy the elements or the compounds in the spices that make them valuable to us. So they are irradiated in order to keep us safe. We pump them down pipelines in order to find out where the pipelines are. And in fact, we bleed them into oil pipelines routinely in order to ensure that those oil pipelines are not leaking. And I haven't even got to the millions of medical procedures that take place every year using byproducts from the nuclear industry. So there's a lot of you that might say, oh, well, we can find other ways to produce the power. And I will contest that later in this presentation. But even if you did that, you still need the nuclear industry, because otherwise we would live in a much less safe environment. So bear that in mind when you think about the nuclear power industry. Okay, so on to small modular reactors. Small modular reactors, everybody says, well, what is a small modular reactor? What does it mean? And it's a very difficult question to answer because it's kind of a marketing term that covers a new concept within the nuclear industry. So historically, the nuclear industry has grown to bigger and bigger plants, making benefit of engineering scale. The bigger it is, the more electricity you can produce for the lesser amount of investment and the lesser number of people, and therefore the cheaper electricity. And that has been the focus. And so nuclear plants have been getting bigger and bigger, and they provide the workhorse electricity to many electricity systems around the world. But there are not many of them. So they're built kind of one at a time, and their technology progresses slowly as a result of that. And then a few people started saying that, well, hang on, we could get another economy of scale. We could get the manufacturing economy scale if we built lots of them. And there is a market for lots of smaller ones. So people started developing designs for the smaller ones. And they're now looking at ones that would go from anywhere of about 1 megawatt electric power to about 300 megawatts, which is the IEA's definition of the range. A 300 megawatt reactor is the sort of thing that Saskatchewan is considering, and would produce all of the electricity required by a small town. A megawatt would be a small community of some kind. Maybe a number of them would operate a campus. Simultaneously to going for the smaller designs, because there was money available to look into the options, a number of things are also happening in parallel with looking at the smaller market opportunity, and that is upgrading the technology. So this is trying to show how the nuclear industry's technology has upgraded over the years. And what I've done is tried to put the pictures in at the bottom to show what other technologies were doing at the same time. And it's to make the point that actually the evolution of nuclear technology is quite slow, because you put one in place and it operates for 60 years. So you don't need to change it for 60 years. So our early reactors were being designed when you had a TV screen that you could just about notice and still had telephones sticking on the wall. Small modular reactors are being designed in an era where you can buy a robot that will act as a servant in your house, and you have a TV screen the whole size of your wall, and a telephone that is also a calculator, that is also a camera, and a recording device and a music player and everything else. So the environment in which small modular reactors are being designed is very, very different to the early plants, and incorporating very, very different technologies. So the evolution is that some of them, and we're going to talk about some, are generation 3+. They are the original generation 3 reactors, but then with a number of new concepts in to make them cheaper and safer and easier to operate. And then some of them that I'm going to talk about are generation 4, which are revolutionary designs using different fuels, different coolants, and having very different characteristics. The government has just finished having a hearing about small modular reactors. I'm not going to go through each of the individual points, but basically, I think it was a Senate hearing and everything was very positive. They all agree that this is an area of investigation that Canada should move forward with, and the concept should be given all of the support it requires to move it forward. I've left that in there so that people can go back to the slide if they want to see what the other recommendations are, or of course they can go to the Government of Canada website and see all of the details there. These though, I'm going to read out the overall conclusions. The conclusions of the committee are that SMRs have lower electricity generation capacity, but their economic model seeks to reduce the cost of electricity generated by limiting their construction cost, which is what I explained. The simplified designs of SMRs, their mass production at dedicated plants, their modular installation directly on site, and the simplicity of their usage should help reduce their installation and operating costs. That's the objective. The economies of scale should be achieved by reactor production. Several witnesses estimated that in these conditions, the cost of electricity generated by SMRs should stabilize around 10 cents a kilowatt hour, which is, probably a little bit more expensive than people are used to now. But if you're not allowed to use the cheapest ways of producing electricity, I'm afraid that does mean that the cost of electricity goes up. So coal is currently the cheapest way of producing electricity. If you're not allowed to use it, then you're not going to benefit from that low price. Then they made estimates from, witnesses testified to the cost of other forms of electricity, basically gas at 14 cents, wind 15 cents, and solar at 49 to 50 cents. Now, I put those figures in there because I know people are going to ask me about what it's going to cost and how expensive they are and all that kind of stuff. And I want to stress, these are not my numbers, and I am as cynical about these numbers as anybody else. Every situation for electricity production has different circumstances, and the best option in each circumstance will be different, and the cost of power of the various different types in those circumstances will be different as well. So at best, these are a crude cut that kind of give you the range and the feel for where things are going to look, but each individual location will have different economic circumstances. And I would also stress that nobody's built an SMR yet, so these are all estimates. The engineers are pretty good at doing estimates nowadays, and they have very tight mechanisms for the way they do that. But we have to say that they are still estimates. That said, the figures for things like wind and solar are also estimates, and it's not clear what they're meant to cover. There is nowhere in the world that has yet built an electricity system built on wind and solar. Nobody has any idea whatsoever what it would cost. And the reason that is a challenge is that if you imagine, so what they originally did was they said, okay, well, we'll put some batteries in and we'll include them in the cost. And we'll put in enough battery to smooth the supply from our plant while it's operating. The idea being that if a cloud came over, that the battery would cut in and then the solar panel would come back on. So that was their original attempt at, we'll include that cost. Now, most of them make their estimate on an 8-hour battery backup. Okay, so they're saying, if we add the cost of our solar and wind, and we add a battery that'll last for 8 hours, then that's all that you need to supply the electricity that you want. Now, one observation about that is that nobody has ever put in a battery with an 8-hour backup, and we don't know whether it would be possible. So I think the best is like Australia, where they've got maybe an hour of backup. People use huge amounts of electricity. Now, let's just say that, okay, we have got the 8-hour backup. What does that mean in somewhere like Saskatchewan? Now, here you have to kind of understand weather patterns, and I think you might be subject to them at the moment. But your peak winter day is a day when there is a high settled over the region. The highs are wide and slow moving, and they are cold and clear, and there is no air moving. So on that day, you're going to wake up, the wind power is not going to be there, you're going to have solar power, and you've got 8 hours backup, but you are draining batteries throughout the day because you don't have solar to meet your total demands. You're relying on some of the wind. So at night, you've now got nothing. And 8 hours in, you've got no power left. The next morning, when you wake up, the batteries are empty, the windmills are still not turning, and people start to die. So, these are the consequences of people putting forward these ideas to say, I'm going to try to fool you into believing that wind and solar can carry the whole weight, when there is absolutely no evidence that we can design and build a system that would do that and not protect people from completely running out of power. So it's serious stuff. And, I can tell you two consequences. One is, if you get it wrong, people die. And two is, if you get it wrong and you're in power, you won't be in power again, ever. And if you want evidence for that, look at what happened in Ontario, where we didn't even get to that situation, but we had a Liberal Party that invested way too much in wind and solar, and as a result, went from being in power to not being a party. So, bear that in mind when you think about the significance of making these decisions. On the other hand, one of the things about nuclear power is you can rely on it. It is there when you want it, and you can call on it. It's under your control, and it is fueled for in some cases months, but you can have enough fuel stored on site to keep you going for years. You will not be subject to challenges with the weather. Canada some time ago set out and developed a roadmap for small modular reactors. It's a 3-stream roadmap of 3 different types of small modular reactors. The first, and the one that is most relevant to Saskatchewan, is Stream 1. It's a machine of around the 300 megawatt range. So it's to connect to a grid and operate something of scale. And the idea was that it's one that we would be deploying fairly soon in order to start trying to replace coal and gas plants, and in Ontario to meet the increasing demand of the province. Stream 2 is the ideas that are being developed out in New Brunswick, and there they were looking at ones that would use fuel more efficiently and indeed actually start consuming used fuel. So a little bit of reprocessing, not to produce plutonium, because the technology that they are planning doesn't do that. It doesn't really reprocess in the way that people use the word, in that it doesn't in any way segregate the plutonium. What it does is it takes some of the other things out, leaving the plutonium in there with the bulk of the fuel. So it is reprocessing by the definition of the word, but it is not reprocessing as we have historically known it. And that will take a little bit longer, but it has environmental benefits because it closes the fuel cycle and reduces the amount of fuel that would need to go to a deep geologic repository. And then Stream 3 is the smaller types of small modular reactors that would be for a very small town or a remote community, or perhaps would run a mine site, or perhaps a few of them would be installed on a mine site to run a mine site. And that's the Stream 3. Sometimes they're called micro modular reactors instead of small modular reactors. So that's Canada's plan. And these are the ones that are currently the front runners. This is the one that you possibly need to keep your mind on. Sask Power have indicated that they have an interest in acquiring small modular reactors as a way of ensuring that they can continue supplying power without using fossil fuels. It's a GE Hitachi machine. It's basically a boiling water reactor. There have been, not sure how many were built, but many tens, if not in the hundreds, of boiling water reactors that have been already built and supplied to the world. And they have developed the technology so that it uses basically the same concepts, but the way the engineering design has been done is that they've put the whole fuel and the reactor down underground. So it's much harder for any damage to be done to it, and it's much easier to keep it safe. And they have designed it so that even if all of the power went out and there was no power to the site for a period of time, and it's days, then the water would circulate and would still remove all of the heat from the reactor so that it would not go into a risky meltdown condition. I think I showed, I must have not saved the presentation because I pulled some of these pictures out so that you could look at them in more detail. But those are the ones that Sask Power are contemplating, and they are looking to have them decisions made in the reasonably near future with a view to having them operating in the 2030s. These are the 2 reactors that are being planned in Stream 2 out in New Brunswick. One is a company, ARC Clean Technology, and it is a sodium-cooled fast reactor. So instead of cooling the reactor with water, you use sodium, which obviously melts at a relatively low temperature, and you can use that to move the heat away. It's a much more efficient way of moving heat. and it is a fast reactor, so that allows it to use fuel more efficiently. Over on the other side is Moltex Clean Energy. They're planning a reactor that uses a molten salt instead of water as the coolant, and it also dissolves the fuel into a molten salt in a fuel pin, so that the fuel is a molten salt as well. And that allows it to operate as a fast reactor, and that will be able to consume used fuel as its energy source, reducing the amount of used fuel that needs to go for disposal, and producing energy without the need to mine any more uranium. So the ARC technology one is about 100 megawatts of electric, if I remember correctly, and the Moltex Clean Energy one can be designed in variable sizes, but they are planning a 300 megawatt. So the same sort of size as the reactors that Saskatchewan is planning. And they will come online a little bit later. So they are more innovative technologies using different fuels, using different coolants, and therefore they're going to take a little bit more time to get ready and to be built. A couple of micro-modular reactors that are being considered in the Stream 3. Picture here of the Westinghouse one. You can see they've kind of done a rendition of what sort of size it is, and it's kind of like a shipping container size. Their idea is that this would be delivered on the back of a sink, or it would arrive in a series of modules that basically just come off the back of a truck. You put them down, link them up, and they develop and they produce power, and they then operate for 40 years with a 3-year refueling cycle. So that's their concept. And they use something called a triso fuel, which I'm going to talk about a little bit later on. In fact, both of these use triso fuel, which I'll talk about in a second. The Westinghouse machine is in a design range 1 to 5 megawatts, and USNC are doing something similar. Both have backers. Bruce Power are backing the Da Vinci micro reactor, and USNC are the most progressed in terms of licensing, in that they have applied for a license to do a demonstration of their reactor at Chalk River in Ontario. So those are the small ones following up the chain. And somehow I have managed to fail to save some of the screens some of the slides that I had prepared. So I'm just going to have to fill in a bit. So the concept of triso fuel is, instead of having a large fuel pin with large chunks of the uranium fuel in it, what you do is you have small slivers of it, and then you wrap it in graphite and silicon carbide. And you end up with something about the size of a billiard ball with a small amount of fuel in the middle of it. The concept behind it is that the silicon carbide is very hard, and it melts at a very, very high temperature, so that actually the emissions that take place from the fuel will exceed the amount of the emissions will exceed the amount of temperature rise that the fuel can give at a temperature that is lower than the silicon carbide will break down. So there is no way physically that you can get a meltdown of the fuel, because it's giving off heat quicker than it's creating heat at a certain temperature, and that temperature, at that temperature, it's still contained. So if all of the coolant disappeared and you just left it, then it would still continue to be safe. And that's the concept behind the triso fuel that would operate both of these innovative new reactors. So well, let's see how many slides we've got for the used fuel, because this was the area that changed a lot, and I obviously saved the wrong version of it. But couple of things that people get very hung up on used fuel. So I want to put it in context and deal with some of the stories that are told about it that are simply not true. So one of the things they'll say is that these materials have never occurred naturally. This is simply not true. The world used to be much, much, much more radioactive than it is today. If you think about it, it has to have been, because all of our radioactive materials have over time been decaying since the world was formed. So the world used to be radioactive. It's much less radioactive now than it used to be. About 2 billion years ago, there was enough radioactivity that became concentrated in one area, in Oklo in the Gabon, and probably other places that we haven't discovered yet, that nature ran nuclear reactors, and it ran them for millions of years. And it ran them as a result of having a uranium deposit in which water was flowing through, and the water acted as a moderator, set up the nuclear reaction. The nuclear reaction caused lots of heat, boiled off the water, the nuclear reaction shut, it cooled down, water flowed in, the nuclear reactors started again. And they did that for millions of years and produced all of the byproducts that are produced in a man-made nuclear reactor. And they sit there in possibly the worst environment. Remember, water flows through it, right? And none of that material has ever caused any harm, environmental harm. So these materials have been produced before. We do have an analog model, and it does exist, and you can go and visit it. And in terms of the danger that these materials cause, this is a man pointing at it. So, yeah, sorry, I'm now pointing at my screen because I'm getting excited. But the picture at the bottom left-hand side there is a man pointing at the deposit. So we know that, that the world has seen these materials and it's coped with them. Of course, it's seen plutonium in another form because we rather irresponsibly some time ago decided to let off lots of nuclear weapons in order that we could show each other that they worked, and covered the world with plutonium. And basically, in terms of health consequences, it's made no difference whatsoever. So when people say, oh, we've got to really be scared of this material, then actually the justification for that doesn't really exist. Now, I'm not saying it's a good idea to keep spreading it around, but it's not as unique as people would like to let you believe. And the other thing that they'll tell you is that plutonium is the most toxic material on Earth, which is complete and total bunk. I've put the list of the top 21 toxic materials that I could find on the internet. You'll notice that plutonium isn't there among them. The most toxic material known to man, and it's about 30,000 times more toxic than plutonium, is the toxin that's produced by the botulism. And we use, just to put in context the significance of how poisonous something is, we inject that into people in order to make them feel that they look better. So, yeah, you know, it is a poison. It's a very, very dangerous poison. But if it's handled correctly, it doesn't cause us any harm. In fact, you can go down this list of toxic substances. A surprising number of them are produced by nature. So that next one, the I don't know how to pronounce it, batractotoxin, that's produced by frogs, and entirely organically, no assistance from mankind whatsoever. Some of those other nasties are produced by mankind, but actually the natural toxins are right there at the top of the list. Plutonium barely rates in terms of toxicity, and the other issue is the significance of toxicity is you have to be able to absorb it, and you're very unlikely to ever do that with plutonium in the first place. So that's just to put it in context of how scared you should be about it. It's not to say we shouldn't look after used fuel, and I'm going to tell you how we do, but don't think that it's anything that much more frightening than anything else we have to deal with. What we do with it, this is from a fuel pool from a fleet of nuclear reactors. So the type of thing that you will be looking at in Saskatchewan supporting a small modular reactor would be much, much smaller than this. But basically the fuel is taken out of the reactor after it's come to the end of its useful life. And it is still emitting heat because there is still radioactivity in it. That radioactivity is decaying, that gives off energy, and so they stay hot. So you have to cool them. We put them in pools. It's that technologically complicated. That is water with a few chemicals in it to keep it clean, and it's circulated to take the heat out of it. In terms of the danger, the water is adequate shielding, so that if you look at that picture and you look on the bridge, you can see two people that are on that bridge, not far from the used fuel, because they're completely shielded from it by the water. So that happens, and typically, historically, we've been putting it in the pools for about 7 years before then transferring it from the pools to a dry storage container, where now all of the cooling is entirely passive. So it sits within this container, has a steel liner, a concrete, poured concrete, and then a steel outer. And it has air channels that allow the air to flow through it that will keep the fuel adequately cool. And again, notice that these are sitting there quite comfortably without any maintenance, routine maintenance requirement whatsoever. Over a period of time, yeah, concrete decays, but they can sit there for quite some considerable time. In terms of the danger to personnel, they're entirely shielded, so these people are happily wandering around close to the containers, under no risk from the used fuel whatsoever. So, do we know how to manage it? Yeah, we do, and it's if you know the hazard and you deal with it appropriately, because it's a solid, it's relatively easy to look after. So we have these not in order. I'm going to talk a little bit about what we're planning. So this is relevant to small modular reactors because they will use the same disposal route for their fuel as is going to be used for the fuel that has been supplying all of that electricity that we talked about at the beginning. We are looking to put it in a deep geologic repository, about 500 meters underground in stable rock deposit. That way, it remains safe, not just while we can look after it, because we know we can look after it. It's never done any harm to any Canadian. And so far as I know, used fuel in storage has not done any harm to any human being. And it does no environmental damage outside of the physical footprint, which is really pretty small. The idea of the repository is once you put it in a repository, society could collapse and we could fail to be able to look after it whatsoever, and it would still make no difference to the livable environment, to whatever remained behind after our society collapsed. So we're looking at 2 sites presently, both of them in Ontario, one near Bruce Power in South Bruce on the Bruce Peninsula, and one further north, close to a town called Ignace. So we're looking at the deep geologic repository. And this is the concept behind it. So there will be a small set of workings on the surface. There will be a shaft that goes down between 500 and 600 meters, depending on where they find the most suitable rock. And then they will be laid out constructively in bays within that area. The used fuel bundle, the used fuel itself is a solid, it's a ceramic. So think like your plates, except actually a much denser ceramic and much, much harder. That ceramic is then held in a metal fuel pin. So that's a solid that wraps around the solid. And then that is going to be put into a steel container, another solid, and that steel container is going to be coated with copper to prevent corrosion. That container is then going to be put into a bentonite box, and that is then going to be put into the rock. So despite the fact that it's a long way away from us anyway, and actually isn't anything all that different to things that we deal with in terms of what can escape from it. We're going to go to all of those measures to make people feel comfortable that it's never going to go anywhere. So unlike Oklo, which had water flowing through it, this will be dry, and it will have all of these engineering measures to additionally keep the materials safe. Now, yeah, so why should we get on and do it? So this I wanted to show this one because I use this in my presentations. Those are my daughter's hands. And when I was in Saskatchewan, one of the things we absolutely loved was the Children's Festival that takes place in early summer in Saskatoon. And one of the mining companies comes along and they dump a whole load of shale and rock and stuff underneath a tent. And you go out there and you can look for fossils. And I always remember, because I was ignorant of these things, I went up there and I looked at the signs and it said, you know, you might find a shark tooth. And I thought to myself, yeah, that's never going to happen. That's, you know, 1 in a million. My daughters and I found 7 shark teeth. And they are not fossils of shark teeth. They are shark teeth. And I am not joking. You can take one of those teeth and you can cut paper with it. It's 70 million years old. That's how slow things change underground. And that isn't even in good rock. We're talking about putting the used fuel in good rock. So things happen really, really slowly underground. And I said something, and I'm going to try this on you, because, you know, I'm not quite as sure of the effect, but I think it's, for me, one of the great justifications to get this job done and to get it done now. And that is actually, we don't know how long society will last. So, you know, we've just had a blast of a virus that, you know, scared us all. It could have been much worse. And we're now facing a war in Europe that none of us ever expected. These things happen on the surface where things happen quickly. We should take responsibility for the used fuel, get our repository built, and get this stuff put underground where things happen very, very slowly. So not quite relevant to the discussion, but it's one of the points that I want to make to people, that this is something that we should feel a moral responsibility to get done and get on and get that project going. So talked about that. And I think I have no idea how long I've gone on for, whether the timing is right, but my excuse here is if I'm too short, then there's plenty of time for questions. And if I've gone on for way too long, I've probably answered most of the questions. So either way, I wriggle out of whatever I've managed to achieve here. But I do thank you for listening, and I hope that I have managed to address some of your concerns.
Well, thank you, Dr. Alexander. Very interesting presentation, and we're not surprised at that. I'm looking for questions in the chat. First one from Ray Johnson. Hi, Ray. Ray and I were stuck in a blizzard together in about 1977, I think. Why are the costs of renewables so tough to pin down?
Yeah, no, I saw that one, and that's an excellent question. So thanks, Ray. So the first thing I'd say is I try not to use the terms renewables, because it's not really the issue that is the differentiator. So if you look at hydro, if you've got a dam and you've got a lot of water, then you can produce electricity from it. And it is a reliable bank of electricity. Like in Quebec, they do have some problems because their dams freeze up and they have issues like that. But generally, you've got a good supply that is under your control. So I've started trying to encourage people to think in terms of reliables and unreliables, which is really what the question's about. And the unreliables are the ones where you don't know when you're going to have access to them. So they're things like wind and solar. And I guess wave, but waves are reasonably reliable. So it's wind and solar are the ones that come on and go off. And the challenge you can work out what the cost of connecting them to the grid is, and that can work out quite cheaply, but they're only available when they're available. You can't rely on them. The challenge comes in working out how much it would cost you to do it if you wanted to have a reliable supply of electricity. And that gets you into what are the weather patterns going to do? How can can you rely on the weather patterns? And I can tell you that just at the moment, you can't rely on the weather patterns. You can blame it on whatever you like, but where I live, and I'm acutely conscious of this, we have had 400-year storms in the last 2 years. So, something's going on. And our ability to rely on what used to be the weather pattern is challenged. Now, so why is it difficult? Well, you don't know how long you're going to have to run the power for, and you don't know how the batteries are going to perform and how you're going to get electricity flowing in and out of the batteries. And that makes a difference to the cost, because now you've got, when you put your first windmill onto the grid, it's contributing whenever it's contributing. But now you're going to have extra windmills that only contribute occasionally, even when the wind is blowing, because you need them to charge the batteries. And nobody's ever done a model that shows, how can you guarantee that you're always going to have electricity and you've got enough stuff to charge the batteries and enough battery capacity to stay charged. And that's why nobody's done it, right? And the people that have made inroads into trying to do that have not been very successful. So you have the German program that inspired Ontario to go the route that it went, and it's been largely a failure. Like it was, ironically, for a long time, I was saying that the German wind and solar program was being sponsored by Putin because it meant that he could control Europe. And it turns out that that's exactly what was happening. So without gas, they found that they had a real problem, and now they're building coal again, which is pretty much the worst thing that they could be doing. So that was a country that tried to do it, not very successful. Most other countries that have tried are similar sort of circumstances. It's just a really difficult thing to do.
Great, thank you.
Yeah, I was just going to check that was enough of an explanation, because it's quite a difficult thing to explain. You have to get this idea of power flowing in and out of the batteries when it's available and when people are demanding it. And I would say that, things are going to get worse, because if we start heating with electricity, either using heat pumps or direct electricity, then the swings in power demand are going to increase. Those peaks are going to get bigger. And not least because people will be turning their and using their heat pumps more when during those cold periods, but heat pumps become less efficient when it gets, air source heat pumps become less efficient when it gets cold. So you've got a double whammy of an increased demand as people try and heat their houses, and the fact that the machines that they're using to do it become less efficient as it gets colder. So the demand is going to be, the cycles are going to go up quite dramatically, making it even harder to work out how to balance a grid unless you've got control of the power that you're putting into it.
Okay. I'm just laughing because this isn't a short question and answer.
Oh, right. Yeah. I'm glad you're reading them.
Well, we've got well, they're starting to come in. So, so the question is from Chris Ford. Thank you, Chris. Is it not better to immediately replace conventional fossil fuels with solar, put it on people's houses right away? It doesn't solve the base load issue, but does drastically reduce CO2 emissions. Or another solution would be spending money on insulating homes, etc.
Yeah, so I'm inclined not to answer that, because it's a whole load of political, socio-political issues that are not related to the technology. So, can you force people to do this? How much is it going to cost to do this? How much are people prepared to do it? I would, and so, yeah, you might be right. It might be, if we can get people, I mean, emissions are a serious problem, and we are not addressing them at the moment. We are playing lip service to them. The world's emissions are continuing to increase. Over the last 10 years, despite all of the talk, emissions have gone up year after year. I think that's correct, Margot. Correct me if I've got it wrong. And it looks like they're going to continue to do that. So we do need to start taking them seriously. And we might have to introduce measures to do things quickly and then have a plan to replace that as we go on to secure it. But I don't think it's for me to answer. I think that's a socio-political question that I'm not competent to comment on.
Okay, thanks for that. Next question.
I spent a lot of words not commenting that, didn't I? I'm contemplating going into politics. The next question I'm going to answer by saying, that's a very good question. Let me answer it this way and give you an answer to a completely different question.
I think Sarah Palin already did that. Question from Vicky Obedkoff. Ontario was debt-free until it went nuclear in the 1970s. Billions of dollars of debt was created that taxpayers are still paying down. But hydro from Quebec can be imported for less than half the cost of nuclear power. Transmission lines aren't that expensive to put in. Why wouldn't Saskatchewan import hydro from Manitoba instead of the enormous cost to the public to go nuclear? And also,
I do not know the answer to that question. You would need to ask the people at SaskPower. I can tell you about what nuclear could do for you. But yeah, I think generally, as I said at the beginning, I'm not telling everybody they should have nuclear reactors. I think that every location around the world will have a different optimum solution. And I can say that in terms of Ontario, there have been a lot of people saying, well, why doesn't Ontario buy from Hydro-Quebec? It would be cheaper than building nuclear. But we get back to that weather issue in that, yes, Quebec's hydroelectricity is very cheap in the summer when they've got lots of it and nobody needs it. But in the winter, they actually run out and they're pulling power in from Ontario. So during the winter when we would need it, that electricity wouldn't be available to us. And that's probably what's driving the government to say, we need nuclear, we can't rely on hydro. It could be a similar issue between Saskatchewan and Manitoba. I do not know. You'd have to ask SaskPower.
I think that's the
in terms of the debt issue, electricity economics are extremely complicated, and you can pretty much make up any number that you want. The fact is that the entire Ontario economy is driven by those nuclear power plants. How much we paid for the electricity and what they cost us is largely an irrelevance. Ontario exists because of its nuclear power plants. If we didn't have them, we wouldn't have the taxpayers to worry about these things. So you can look at these things a number of ways, but basically the availability of reasonably priced electricity is what built Ontario into the manufacturing powerhouse that it is today. Without those nuclear reactors, we would only have been able to do it with coal, and that would have been pretty disastrous in terms of our emissions to the world. Making that point there's another point that's kind of not relevant to the presentation, but I think is important for people to understand. If we decarbonized all of Canada completely, the world would barely notice. We, as individuals, we produce a lot of carbon dioxide, but as a nation, it's not all that significant. And so, focusing just on what we do at home isn't all that relevant. One of the reasons I was excited about small modular reactors is that we can use them in the developing nations to allow them to develop without having to go through the phase of burning fossil fuels. And that is both an altruistic, I think that's an appropriate thing to do, because I think we've got to help the developing nations develop. But it's also very self-serving, because carbon dioxide is entirely fungible. It doesn't make any difference where in the world it is produced. Its consequence on the environment is exactly the same. So unless we help other nations develop emissions-free programs, then we are not going to solve the world's problem. And as one of the world's leading nations, I think we have an obligation to develop and demonstrate technologies that they can use to solve their problems. And that's why I'm so excited that Canada is taking a leading role in small modular reactors, because once we've demonstrated them, we've shown that you can put them in a previously non-nuclear community and operate them safely and effectively, then we can go and do it in Africa, where the populations are expanding very, very rapidly, and they are going to need electricity in order to develop. So that's something to think about. It's not relevant directly to Saskatchewan, but if you want to stop climate change, it's not just in Canada you have to stop it. You have to help the rest of the world as well.
Okay, I'm going to.
Margot, correct me if I'm wrong, Margot.
Vicky's got a second question, but I'm going to jump down to another one. We'll go back to Vicky if there aren't others. From Ann Coxworth, it's where do you think the factory of manufacture? By the way, I had cataract surgery last week, and I can't necessarily read well. Where do you think the factory to manufacture a whole lot of SMRs would be located?
Sorry, what was the final part of it? It was just where it would be.
A factory to manufacture a whole lot of SMRs would be located.
I don't know the answer to that question, so it's down to whoever makes the best offer to try and get the factory located near them. So I'm sure those discussions are taking place, but they could be manufactured anywhere. Obviously, economically, you would want to put it somewhere that has reasonable access routes for shipping large pieces of equipment.
Okay. Go back to Vicky's question. Second question. Alpha emitter plutonium-239, if breathed in as a dust, is very dangerous and carcinogenic. It has been estimated that a pound of plutonium inhaled would give cancer to 2 million people. Where are you drawing your information from that alpha emitter plutonium is not a human health hazard?
Okay, so this is a delightful question, because it's also been estimated that 1 bucket of water can kill 10 million people. You have to look at the context. So yes, it may be true, that statistic, but you are never going to be exposed to inhalation of plutonium. The plutonium is contained in solid fuel pellets, a ceramic like a plate, but more dense and harder. And unless you go and lick it, which you can't do because it's so radioactive you couldn't get close to it, you are not going to be able to inhale plutonium. So yeah, it's an interesting statistic. It's an entirely irrelevant statistic, and not one that you should worry about. I didn't say that plutonium is not a health hazard. I said that it's easy to manage, and it is not the health hazard that people try and make it out to be. It's no different to other health hazards that we routinely manage in our modern world. That's the point I was making, not that it isn't a health hazard, but I will make the point that you will never be exposed to it because there is no route to exposure. So stop worrying about it.
Good question from Karen Kolanko-Evian. Do SMNRs have to be located near a surface water source?
They don't, but it's very preferable that they are. So some have been designed to use air cooling, but air cooling is very inefficient. So now you're using a lot of the electricity you produce to produce the cooling that's needed to drive the turbines. And if you do that, then you've got a large parasitic load, you're not producing as much electricity, so you're paying a lot more for the plant. So theoretically, you don't need to put them near water, and some are being designed so that you don't have to, but it's very beneficial to use water as a cooling source because it is so efficient as a coolant.
So I'm going to jump down to Chris Ford has a question. Chris Ford's got another question I was going to read, but this one follows from Karen's question. So similar to Karen's question, would you want an SMNR built on Lake Diefenbaker, the water source for 70% of Saskatchewan residents?
Yeah, I wouldn't see any problem with that whatsoever. There is not a circumstance I can conceive of where you would necessarily have any significant quantities of radioactivity ending up in the water. So I wouldn't see that as a problem whatsoever. If you could find a circumstance where that happened, it's actually pretty easy to take out of the water. So you still wouldn't have a problem, even if the worst did happen.
Chris has a multiple part question here. Uranium supplies are finite. Current rates of consumption has 84 years. Start replacing conventional, I assume electricity production, and the consumption rate will grow quickly, perhaps shortening reserves to 30 years, burdening future generations with the need to maintain the waste for the end of time.
Yeah, so uranium reserves. So again, you have to kind of understand what a uranium reserve is. So the uranium reserves are calculated based on the bodies of uranium ore that we currently know about that would be economic to mine at the current price of uranium, right? So that's fairly clear. Now, if the price of uranium goes up, the reserve volume goes up as well, because you can now mine other places. So yeah, it might be 84 years at the moment, but if we start using that up and the price goes up, it goes up to 200 years. And then if the price goes up again, it goes up to 300 years. The Chinese are looking at extracting uranium from the seawater. There's tons of uranium in seawater. We wouldn't do it at the moment because you can go to northern Saskatchewan and the stuff is there almost as the metal. I'm exaggerating, but they're very rich ore bodies. So we can gain access to those very rich ore bodies. But there's a lot of uranium in seawater, and the Chinese are looking to mine uranium out of seawater. So am I worried? By the time we run out of uranium for fission reactors, we will have found better ways to produce electricity. I'm fairly confident of that. If we fail to do that, then the two reactors that I talked about that are being designed out in New Brunswick, they're fast reactors, much more efficient use of fuel, and the potential to use up stocks of the used fuel. And there's something like 1,000-year reserve already in existence in Canada. So it would be a different style of reactor if it looked like we were running out of uranium, but you could still run nuclear power if you needed to. Basically ad infinitum.
And a follow-up with Chris is talking, he says the burial procedure sounded fairly energy and cost intensive. Are those factored into the kilowatt hour calculations?
So there is like a tax put on every kilowatt hour of nuclear electricity produced in order to pay into a fund to pay for disposal. So it has been included in all the costs of calculating nuclear electricity if it turns out that we can build that repository at the price we expect to. And it's fairly robust to that. I mean, it's not like we haven't mined before. So the estimates are going to be pretty good. And as long as the money earns on the financial markets what it is expected to, then we have more than enough money to carry out that disposal. And it's included in the current price of electricity.
Okay, and I will note there are comments in the chat. I suggest people, take advantage and look at those and read those. I'm not planning on reading those out. Question from Elizabeth Klein. How do you justify going ahead with building hundreds or even thousands of small nuclear reactors when there's no proven way of securely dealing with the radioactive waste, i.e. spent fuel rods containing structure for thousands of years?
Yeah, so there's no secure way of disposing of anything that mankind produces. Most of it we just throw onto the surface and hope for the best. We do that with toxins of equivalent danger to the ones that we're dealing with used fuel. When we say we can't prove that it'll be safe for thousands of years, then you know, it's what you require as proof. I mean, one of the slides that did get lost is a breakdown of what is in used fuel. And I think the thing to remember is that 99% of it was dug out of the ground in the first place. And it was dug out of the ground in places where water did have access. So if you go to northern Saskatchewan, one of Cameco's mines, they had to put freeze walls in to stop a water flowing through the middle of the ore body. So it's not like any of these materials have not been exposed. We haven't been exposed to them in nature before. So that's why I was trying to get people not hung up on how different these are. 99% of it came out of the ground in the first place. And all we're doing is putting it back into a safer environment than it came out of. So yeah, I have no problems. I have no problems. And again, in terms of calibrating the problem, do you want to fry the world in the next 100 years? Or do you want to have a problem in 10,000 years' time that probably will never be a problem that anyone will notice? And I think, you know, that's a question that people need to start asking themselves. We are making no progress. We need some heavy hitters, and we need them soon to start producing not just electricity to replace our existing electricity supplies, but the electricity that will replace heating and transport and industry. And it's a lot. So as far as I can tell, you look anywhere in the world, the wind and solar programs have made essentially no dent on our production of greenhouse gas emissions. We've got to do something big, and we've got to do it soon.
Okay, I'm going to pose a question because I posed the same one last time.
Right.
And
sounds like a difficult one.
No, I don't know. It was one that's always interested me. And I wasn't even sure if it was still there, but if you look at my home insurance policy, buried down somewhere, there is a clause saying that I have no coverage in case of a nuclear accident. And so my question last time was, so why is that?
Right, that's a really simple one. It's because the government covers you. So they've assumed that risk. You don't have to worry about it. So the insurance company is just saying, I'm not covering you for it because you're already covered.
Okay.
You know, it's not because it's such a great risk or anything like that. It's simply because it's dealt with elsewhere.
I've got follow-ups, so I'm not going to ask them. I'm the host.
Good, but by all means do. I wouldn't like to or call me afterwards. I wouldn't like to leave you not clear on the
Well, I think we got the same answer in the long run last time. I just find it ironic that I can get earthquake insurance.
Yeah, but the government doesn't cover you against earthquake insurance.
I know. Well, maybe they should.
Well,
Save me some money.
Yeah, well, that's an interesting philosophical discussion, and I'd love to have it with you, but it doesn't impact us here today.
Okay, and I think this will be maybe not the final question. I've got two questions, and then we're going to cut it off. One from Ann Coxworth. Your list of relative toxicity of different materials seems to be limited to chemical toxicity. How would it change if you included radio toxicity?
Yeah, it's difficult to tell. From what I can tell, plutonium is a toxic material as well as being a radiotoxic material. And what difference does the two make, right? It's not clear to me. I don't see why people worry so much about the radiotoxicity. In order to be harmed by plutonium, you have to ingest it. It will have a chemical toxicity and it'll have a radiotoxicity. there are a lot of things more toxic than plutonium, as we've already seen. People get hung up on the radioactivity side of it, and I'm at a loss to understand why.
I'm actually going to allow 2 more questions and then we're going to cut it off. One is, do you feel nuclear gives a license to keep carrying on with our irresponsible manner of living?
Oh, wow.
I thought it was interesting.
I'm going to answer that a different way. I think anyone that is relying on human beings changing their behavior and reducing their living circumstances in order to deal with greenhouse gases is probably fooling themselves. And therefore, we have to find some way of allowing people to live in the way that they want to live and supplying the things that they need that they're going to do it. And that might be a bit harsh, but if you look at what will happen if you start taking away things that people want, then the people doing it will get voted out of power and they will lose the ability to make progress. So, you know, we have to be rational about the progress that we can make. And any step that punishes people that is too great will mean that we actually go back a step as some other government comes in and says, that was all wrong and we don't need to bother and you can all go and have a party now. So we don't want that to happen. I think we have to take measured steps. And nuclear does allow us to live lives that we are used to without any real impact, other than we'd have to pay for it.
Okay, and last question, we're down to an hour and 27 minutes here. Does the war in Ukraine have any lessons about the safety of the use of nuclear reactors? And thanks from Robert Renier for that one.
Yeah, well, the first one is the observation I was making earlier. It's a very good argument for getting your deep geologic repositories built and getting the stuff off the surface that you don't need on the surface. So let's get behind that as a campaign and get that done. Yeah, no, it's very difficult. You know, there's kind of 2 lessons and we don't know what the outcome is. One is that nuclear power plants are so important that people will, to some extent, avoid having wars near them. And therefore, they are a sort of strategic benefit in a warfare circumstance. And they're quite hardened so that while they're producing, they are continuing to supply electricity to the region. The other is, of course, they are a risk. And you know that if mankind wants to forcibly cause harm to a nuclear power station, then they can do that, and that is you know, one of the consequences that we have to understand and decide how we're going to deal with. There is no, you know, unless you have a complete lunatic, and tragically it might be the case that we do, then there is no strategic benefit to taking out a nuclear power plant. Because if you're trying to invade a country and you damage the nuclear power plant, then you've just invaded a country that isn't much use to you. So, you know, I think that was the logic behind a lot of it. I don't think anybody had actually planned on having, you know, somebody that didn't behave in a rational fashion running a major country.
All right. Well, thank you very much. I'm going to quote Chris Ford in the chat. He says, thanks very much for your thoughtful answers and explanations. And
I think I failed on the plutonium thing, and it's a very on the toxicity thing, and it is it's a very difficult thing to explain because people are hooked up on the radiation side of things. And the point I'm trying to make is that you're not going to get exposed to plutonium, right? Because there's almost no circumstance in which you can inhale it or take it into your body. It's locked up in a solid ceramic. It's going to be deep underground. You can't take on large quantities of plutonium. So the risk, whether it's the toxicity risk or the radiotoxicity risk, is very, very low. And the radiotoxicity risk and the toxicity risk are kind of similar, right? And there are other things that are equally toxic. So we talked about americium-241. The point I made about that, chemically very similar to plutonium, not the same by any means, but it's toxic. And we use it all of the time. We throw it into our waste dumps. It's also an alpha emitter like plutonium. So it's kind of a facsimile for plutonium. We just throw that into our landfills. You know, you have to look at pathways. You have to look at overall risk. Just jumping on one issue is not helpful because it doesn't give you the right result. You need to understand all of the issues that relate to the material and manage it appropriately. We are doing incredible environmental harm making solar panels in China. Nobody in Canada cares about it because the environmental damage is in China, but it's still in damage to our planet, right? And we should care about it. It's similarly true with the materials that go into wind power. You have to look at the picture as a whole and say, okay, there's this benefit and this harm, and this benefit and this harm, this benefit and this. How do we weave them together in order to produce the optimum outcome for the world, and not have this black and white, oh, I'm scared of this, so we should do none of that, because quite often it's the safest thing to do. You know, if you look at damage statistics to human health, nuclear is actually quite low on the list of power generating technologies. It's orders of magnitude below coal, and you find coal acceptable in Saskatchewan. It's still orders of magnitude below gas even, and it's on a par with wind, and it's lower than solar. So if you take all the risks into account, you know, you can focus on the risks that come from nuclear power, but you have to look at what the consequences are of not having it. I guess that's the point I'm trying to make.
All right.
Sorry, I went on a bit.
No, always, that's one of the prerogatives of being the speaker. You get that opportunity to clarify and to add something you thought might have been missed. So I'd like to, again, thank you very much for your time today and thought-provoking presentation. I will note that we have recorded it, and our hope is to get both this one and the one we had last week up on our YouTube channel. So there are people who've said to me, you know, I just can't make it tonight. Are we going to be able to look at that? And they're hoping to do that later. So that sounds absolutely great. I'd like to thank the people who came tonight and put in their time to listen. This is an issue that, you know, has been discussed, I think, a fair bit, but not at least within our circles to the depth that we've had in this series. And maybe at one point I thought to myself, oh, we need a series 3 on this one, and maybe a part 4. Somebody has suggested that we do a session on geothermal, which would be an interesting piece to do as well. So we may get there. So
geothermal fits into the category of reliable energy production. So I think it is something that people should be looking at very carefully.
There we go. All right. And when you said, you know, you in Saskatchewan don't seem to mind coal, those aren't the people that are here tonight, I assure you.
Well, you know, and so a quick observation on that, right? As I said, carbon dioxide is fungible. One of the things from a socio-political point of view, I wish the world would start thinking about is how we make progress quickest. So there are jobs dependent upon coal that is already being mined in Saskatchewan, and it is producing emissions. And we could cancel out all of the investment in the plants that's been made, and we could destroy all of those people's jobs in society. We could also invest in putting a nuclear plant in a country that's developing that hasn't built its coal plant yet. And from a CO2 point of view, the consequence would be just the same, but we might be using our money more efficiently. And that's the result we want. We want to get to the fastest route to reducing our emissions. It might not be just doing it at home. It might be investing in doing it somewhere else as a more efficient way of using our dollars. So that's a good thing to think about from both a self-serving and altruistic point of view.
Thought-provoking indeed. All right, thank you very much. Thanks, Dr. Hurlbert, for providing some comments in the chat and providing a stellar introduction tonight. And I'm going to wish everybody farewell.
Great. Thank you very much. Appreciate you talking to you.
Good night.